Commander, let's light the sky. Training sharper drone pilots, learning how to fly. Mission ready mindset, safety leading every plan. Skills that build confidence from takeoff through the scan. Tune in at Sky Commander, come join the crew today. Learning smart, fly with purpose, level up your way. We see more, no sooner, that's the edge we're here to spread. See above, go beyond, get ahead.
Okay, let's get started. Picture this for a second. You're standing perfectly still on a sidewalk.
Right.
And you're looking up at this pristine, hovering machine, maybe like 150 feet up in the air.
High up there, yeah.
Exactly. You are flying this highly advanced, super expensive professional camera drone over a really bustling downtown street.
Which is always stressful.
Oh, completely. It is a true urban canyon. You've got walls of glass and steel, concrete just rising up on all sides of you.
Basically a maze.
Right. And your mission today, the reason you're out there, is to capture this sweeping cinematic tracking shot of a newly constructed skyscraper.
Getting that perfect sunset glare on the glass.
Exactly, the money shot. And honestly, everything looks completely effortless.
It usually does at first.
Yeah, I mean, the drone is holding its position in the sky like it is literally physically nailed to the clouds.
It's just locked in.
Locked in. The high-definition video feed on your controller is crystal clear, framing the shot perfectly.
Oh, beautiful.
And the client, the person who hired you, is standing right over your shoulder.
No pressure.
Right. They're watching the monitor, nodding in absolute approval. It's a great day.
Until it isn't.
Yeah, because then, very quietly, without any dramatic alarms or flashing red lights or sirens.
Nothing to grab your attention.
Right. Just a tiny little text warning flashes in the very corner of your screen.
And what does it say?
It just says, weak positioning.
Oh, man.
Yeah. And suddenly, the drone just stops fighting the wind. It starts silently and smoothly sliding sideways.
He's drifting.
Drifting directly toward a massive glass balcony.
That is the worst feeling in the world.
It is, because in a split second, the entire reality of your afternoon just changed. You are no longer a creative camera operator framing a sunset.
No, you're not.
You are thrust into a high-stakes, super high-stress aviation recovery scenario.
And that exact split second is the difference between a pulse-pounding near miss that you hopefully learn from.
Right.
And a catastrophic incident that ends up on the evening news.
Oh, for sure.
Because when you're operating in that confined geometry of a city canyon, your margin for error doesn't just shrink. It basically vanishes completely.
It's just gone.
Gone. Surviving that moment is not just about your technical manual skill on the control stick.
It's deeper than that.
Exactly. It's about your human reaction time, your physiological preparedness, and whether or not you have unknowingly fallen into this psychological trap.
The trap of managed flight.
Yes. What the aviation industry calls managed flight.
The stakes here are just incredible when you really sit down and think about the physics of what is happening overhead.
It's a lot of physics.
So the mission of our deep dive today is to really unpack the mechanics of mastering urban drone flight.
We've got a lot of ground to cover.
We really do. We're looking at surviving this terrifying, stomach-dropping phenomenon known in the industry as GPS dropout.
The dreaded dropout.
Right. And we are pulling heavily from the training frameworks laid out in Sky Commander Season 9, Episode 3 for this deep dive.
Excellent source material.
It is. But as we dig into these concepts, it becomes immediately apparent that this isn't just a technical manual about quadcopters.
No, not at all.
It's fundamentally an exploration of the psychology of automation.
How we interact with machines.
Yeah, and the hidden physical traps that cities lay out for these autonomous systems.
Cities are hostile.
Very. And most importantly, I think it's a masterclass in what happens to the human brain when these incredibly smart, invisible machines we trust.
When they just give up.
Yeah, they suddenly shrug, hands the controls back to us without a word of warning.
You know, what's genuinely fascinating about a GPS dropout is that it does not mean the drone is falling out of the sky.
That's a huge misconception.
Massive misconception.
Yeah.
The motors haven't failed.
Right.
The propellers are still spinning. The battery is completely fine.
So it's perfectly healthy.
Mechanically, yes.
Right.
The drone is usually still flying perfectly well, but it has abruptly stopped doing the invisible automatic work of holding its geographic position over the Earth.
It just lets go of the map.
Exactly.
Yeah.
The aircraft drastically changes its behavior, and the pilot's brain has to catch up to that new physical reality instantly.
That cognitive lag.
Right. If your brain fails to update its mental model of what the machine is doing in that exact second, you will take a highly recoverable technical glitch.
And make it worse.
You'll inadvertently turn it into a physical collision.
Man. So the drone is fine. It's the environment and the automation that have shifted.
Exactly.
To really understand why a drifting drone is so incredibly dangerous in that split second, we first have to understand why you, as the pilot, felt so completely and totally safe just 5 seconds earlier.
Right. Why were you so comfortable?
Yeah. It all comes down to how modern automation creates this massive, comforting, false sense of security.
It tricks you.
It does. It's the critical difference between experiencing managed flight and possessing true mastery of an aircraft.
And, we have to be fair to you as the pilot here.
Yeah, give the pilot a break.
Right, because modern camera drones are incredibly sophisticated pieces of technology.
They really are.
They are engineered specifically to make you look like a much better, much smoother pilot than you might actually be.
They flatter your skills.
Oh, absolutely. In normal GPS-assisted flight, the drone is doing an astonishing amount of invisible, microscopic work on your behalf.
Like what kind of work?
Well, the flight controller is calculating data thousands of times a second.
Thousands. Wow.
It constantly monitors its position. If, say, a 5-mile-an-hour crosswind hits the drone,
Which happens all the time.
all the time, the flight controller automatically increases the RPM on 2 of the motors to lean the aircraft slightly into the wind to fight it off.
So it's actively leaning.
Yes, completely automatically.
Yeah.
When you push the control stick forward and then suddenly let go, you don't just coast.
Right. It stops on a dime.
Exactly. The drone aggressively pitches backward, acts as an air brake, and parks itself rigidly in the sky.
It's so crisp.
It stabilizes the hover perfectly.
Yeah.
And it does all of this completely in the background.
So as a pilot, you don't see any of that effort?
No, you experience this as a rock-solid, perfectly stable platform.
And you think, wow, I am amazing at this.
Right. You naturally think, wow, I am really flying this drone. But the reality is you are merely guiding it.
Guiding it. That's a huge distinction.
The drone's computer is the one actively managing the flight.
That distinction changes everything. You're guiding, the drone is managing.
Precisely.
And the primary tool the drone uses to manage that crisp, robotic position holding is something we just casually call GPS.
Yeah, everyone says GPS.
But if we're going to be precise here, and in an urban canyon, precision is everything.
It really is.
We really shouldn't be calling it GPS, right? We should be talking about GNS.
Right, GNSS.
Let's break down the mechanics of what is actually keeping that drone nailed to the sky.
It's an important technical distinction for sure. GPS, or the Global Positioning System, is actually just one specific constellation of satellites.
The American one, right?
Right, owned by the United States government. Calling all satellite navigation GPS is a bit like calling all facial tissues Kleenex.
Oh, that's a great way to put it.
Yeah. In reality, modern commercial drones utilize GNSS, which stands for Global Navigation Satellite System.
Okay, so it's a broader term.
Much broader. GNSS is the overarching network that includes the American GPS, sure, but also the European Galileo system,
Okay.
the Russian GLONASS, and the Chinese Beidou system.
Wow, so it's pulling from everywhere.
Exactly.
Yeah.
It is this massive, redundant family of sky breadcrumbs that the drone looks up at to figure out exactly where it is in 3-dimensional space.
So it's pulling data from multiple global systems simultaneously to get a fix.
Yes. The drone looks up at these constellations and listens for the radio signals ticking down from space.
Ticking down. I like that visual.
Yeah, and by calculating the exact microsecond those signals arrive, the drone uses trilateration to pinpoint its exact latitude, longitude, and altitude.
It's doing all that math constantly.
Constantly. When that GNSS signal is strong and it has a clear view of the sky, the drone locks itself to that specific mathematical coordinate.
Like it's tethered to a dot.
Right. If wind or momentum tries to push it away from that coordinate, the motors just automatically fight back to stay on the dot.
Okay, so that GNSS network is the invisible safety net.
The absolute safety net.
It's the tether holding the drone in place. But what actually happens mechanically when that net breaks?
That's the scary part.
Yeah, when the drone can no longer see those satellites, it enters a state called ATTI mode, right? Attitude mode.
Yes, ATTI mode.
And the crucial thing here is that the drone doesn't break.
No, it doesn't
It
break.
doesn't drop like a stone. It just changes the rules of physics you're playing by.
Exactly.
So what exactly is the flight controller doing? And maybe more importantly, what is it not doing when it drops into ATI mode?
Well, when you lose that GNSS lock and drop into ATI mode, The internal gyroscopes and accelerometers are usually still functioning perfectly.
So the internal sensors are good?
Right. The flight controller is still working to keep the drone level. It stabilizes the pitch and the roll, so the drone isn't going to just flip upside down.
Okay, that's reassuring at least.
Yeah. And it usually also maintains its altitude using an internal barometer that measures air pressure.
Oh, it measures air pressure to stay at the right height.
Exactly. So to be clear, the drone is upright, it is flying, and it is holding its height.
What?
But because it has lost its connection to the satellites, it is no longer holding its horizontal position over the ground.
Wow. So it's basically blind to its place on the map.
Precisely. It knows it is level, but it has no idea where it is geographically.
Right.
So if a gust of wind hits the drone, it will simply drift with the wind like a balloon.
Just completely at the mercy of the wind.
Exactly. Furthermore, if you are flying forward at, say, 20 miles an hour and you let go of the control sticks.
Normally it would break.
Right. But in ATTI mode, the drone won't automatically apply reverse thrust to brake and stop in place.
It just keeps going.
It'll just level out, and its forward momentum will carry it coasting through the air.
Until what?
Until aerodynamic drag eventually slows it down, or until you, the pilot, manually pull back on the stick to arrest that momentum.
Man, you know, the way I constantly visualize this shift is through this concept of the ice rink.
Oh, the ice rink analogy is perfect for this.
It really is.
Right.
Because flying a drone in full healthy GNSS mode is exactly like standing on dry, high-friction pavement in a pair of really grippy sneakers.
Right, you have total traction.
Yeah, you want to walk forward, you take a few steps, you want to stop, you just stop moving your legs, and your feet stay firmly planted exactly where you left them.
We're locked to the ground.
Exactly, locked to the ground. But dropping into ATTI mode is like suddenly, without any warning, standing on a freshly polished, frictionless ice rink.
And you're wearing normal shoes.
Right. You can still stand upright. You haven't fallen over.
The gyros are keeping you up.
Exactly. But if you were already walking when you hit that ice, your momentum is going to keep you sliding forward.
You're just gliding.
And if someone comes up and gives you a shove...
Which is the wind.
Right, which is essentially what a gust of wind does to a drone. You are going to slide sideways, helplessly. And to stop, you can't just stand still. You have to actively dig in your skates and fight your momentum to come to a complete halt.
It takes manual effort.
It takes so much effort. But let me challenge the design philosophy here for a second.
Sure, go for it.
If I am a professional pilot, right, and I spend thousands of dollars on a highly advanced automated piece of technology.
They are not cheap.
No, they're super expensive. And it suddenly just throws up its hands and turns the sky into a frictionless ice rink.
Okay.
Isn't that fundamentally a failure of the manufacturer?
I hear this complaint all the time.
I mean, isn't the machine giving up on me right when I need it most?
It is completely natural to feel that way, but that is exactly the psychological mindset you have to completely dismantle if you want to fly safely in a city.
Really? So it's not a failure?
No, the drone isn't giving up on you. It is simply encountering a physical environment where its sensors can no longer guarantee mathematical accuracy. Think about the alternative here. If the drone kept trying to use corrupted, bouncing, or weak satellite data to hold its position,
it would be guessing.
Worse than guessing, it would be acting on false reality. It might think it has suddenly teleported 50 feet to the left.
Oh, because the signal bounced.
Right. And in its attempt to correct this false error, it might aggressively fly itself full speed into a concrete wall.
Trying to get back to where it thinks it should be.
Exactly. So automatically dropping into ATI mode is actually a brilliant safety mechanism.
It's failing safely.
Yes.
Yeah.
The computer's essentially saying, I can no longer trust my sensors, so instead of making a dangerous, unpredictable move, I am handing manual control back to the human.
So it's defaulting to human judgment rather than flawed algorithm judgment.
Exactly. And what is so crucial for pilots to understand is that dropping into ATI mode does not suddenly create weak stick skills in a pilot.
It doesn't.
No, it merely exposes them.
Wow, it just strips away the disguise.
Yeah, you find out exactly how good you really are in that 1 second.
That is humbling.
You do, because for the entire flight up until that moment, the automation was masking the effects of the wind.
Covering for your sloppy flying.
Masking the physics of momentum, exactly. As a pilot, you have been enjoying this incredibly comfortable, low-stress relationship with the aircraft.
Yeah, sipping your coffee while you fly.
Right. But that relationship is built on a fundamental psychological assumption. You implicitly believe, this machine stays exactly where I put it.
And when it doesn't.
When the aircraft suddenly slides on that ice rink, you aren't just dealing with a moving piece of plastic and carbon fiber.
What are you dealing with?
You are dealing with the sudden, jarring collapse of an assumption.
It's cognitive shock.
Yes, you realize in real time that you haven't actually been flying the aircraft at all. You've only been supervising it.
Wow.
And suddenly, supervision is no longer enough to keep the machine safe.
And when you talk to veteran operators, they always describe this incredibly visceral, uncomfortable feeling that happens right before the app on the controller even flashes a text warning.
Oh yeah, they know before the app knows.
Right. Long before the screen says weak positioning, pilots talk about this deep gut feeling when the drone suddenly feels soft in the air.
Yes, soft is the exact word they use.
Or they describe it feeling like the drone kind of floats at the end of a movement instead of locking in.
It loses that rigidity.
It's like the crisp, robotic responsiveness of the controls just evaporates right in your hands.
Yes, and that gut feeling is a highly tuned human response.
So it's real. It's not just their imagination.
Oh, it's very real. Your brain is actually processing subtle visual cues and physical latency much faster than the drone's diagnostic software can process the data, format it, and generate a text warning on your screen.
That's incredible. The human brain beats the processor.
In this specific way, yes. You let go of the forward stick, and instead of that crisp robotic stop you're used to, your eyes see the drone glide just an inch or two further than it should.
Just a tiny bit of wander.
It wanders. It feels loose. That softness is the exact physical moment the invisible hand of the GNSS network lets go.
And what happens if you ignore that feeling?
If you ignore that gut feeling, if you doubt your own eyes and wait for the app to officially pop up a warning to tell you there is a problem, you have already burned through valuable seconds of reaction time.
And in a city, time is distance.
Time is absolutely distance.
So we have established exactly how the drone loses its position, the physics of ATTI mode, and why the transition from pavement to ice feels so jarring to the human brain.
The internal mechanics.
Right. But to truly grasp the danger of operating in an urban environment, we need to understand where this happens.
An external environment.
We need to transition from looking at the internal computer of the drone to looking at the external physics of the city itself.
Because the city is the adversary here.
Yeah, the training frameworks make it crystal clear. The urban canyon is not just a difficult place to fly, it is actively hostile geography.
It really is. If we zoom out and connect this to the bigger picture of aviation safety, the primary thing a city does is compress time and space.
Explain that. How does it compress time?
Let's compare it to flying out in an open grassy field in the country.
Okay, a nice big park.
Right. If you are flying in a wide open park, your drone loses GPS, and a gust of wind pushes it 3 meters to the left.
Who cares? Right.
Exactly. That drift is simply information. You note it, your brain processes it, you apply a little counter stick to correct it, and absolutely no harm is done.
Because there's nothing to hit.
You have hundreds of feet of empty, forgiving air in every direction to figure out the problem.
Plenty of time to react.
But when you fly in a downtown corridor, a 3-meter drift is no longer just information.
No.
A 3-meter drift is a direct collision path.
Because you're surrounded.
You're moving laterally toward a glass window, a pedestrian on a balcony, a moving delivery truck, or high-voltage power line.
The margins are just gone.
The comfortable margin for error goes from vast to completely non-existent in the blink of an eye. The city squeezes you.
Wow. And to help pilots visualize and manage this incredibly dense, squeezed threat environment, the urban flight training outlines the GLASS hazard stack.
GLASS. It's a great acronym.
It really is a brilliant acronym that details exactly the elements a city uses to try and take your aircraft down.
Let's walk through it.
Yeah, let's break it down. So G stands for GNSS reflection or blockage.
Right.
L is for lines, wires, and lights.
The invisible killers.
A is for airspace and other aircraft.
Helicopters, mostly.
S is for streets, vehicles, and people below.
The ground hazards.
And the final S is for signal, interference, and steel structures.
Electromagnetic mess.
Exactly. Now, I want to dive deep into that first one, GNSS reflection, because it is the root cause of so many crashes.
It's the silent killer.
The curriculum cites actual NASA research on how satellite signals behave in urban environments.
Which is fascinating stuff.
It is. And, you know, my initial thought was always just that skyscrapers block the sky so you get fewer satellites. Like, oh, I'm in a shadow. I have less signal.
That's what most people think.
But it's actually much worse than simply having the signal blocked, right? The city actively corrupts the data.
It corrupts it in a way that is incredibly difficult for the drone to detect until it's too late.
How does it do that?
Well, NASA's research on urban air mobility highlights a severe phenomenon called multipath reflections.
Multipath?
Yes. To understand multipath, imagine you are trying to look at your reflection.
Okay.
If you look into a flat, clean bathroom mirror, you see exactly where you are. That is a clean GNSS signal in an open field.
Direct line of sight.
Right. But now imagine you are standing in a carnival funhouse,
Oh boy.
and you're looking into a cracked, warped, multi-angled mirror.
You look all distorted.
Exactly. The image of yourself is bent, fragmented, duplicated, and arriving at your eyes from completely weird angles.
It's super disorienting.
That funhouse mirror is exactly what a glass and steel skyscraper does to a highly sensitive radio signal traveling down from a satellite in medium Earth orbit.
So the signal is just bouncing everywhere.
Yes. The signal doesn't just hit the top of the building and stop. It grazes the side of the building, bounces off the reflective glass, pings off a steel girder on the building across the street.
Like a pinball.
Like a pinball. And then finally hits the GPS antenna on your drone.
And because the drone calculates its position based on the time it takes the signal to arrive, those bounces totally ruin the math.
Exactly. Radio waves travel at the speed of light, roughly 186,000 miles per second.
So fast.
The drone's computer is counting the exact nanoseconds it takes for the signal to travel from space to the antenna.
Just tiny, tiny fractions of time.
Right, and it uses that time of flight to say, okay, that satellite is exactly this many miles away.
Got it.
But if the signal bounces off a glass building first, it has to travel a slightly longer physical path to reach the drone.
Because of the detour.
Exactly. It might only be a few extra nanoseconds of travel time, but at the speed of light, those nanoseconds translate into massive distance errors.
Oh, because light goes so far in a nanosecond.
Yes. The drone's computer does the math on this delayed signal and suddenly concludes, wait, if the signal took that long to arrive, I can't be hovering over the sidewalk. I must be 50 feet to the right, inside the lobby of that bank.
Wow. And so if the drone is still in GPS mode, when it makes that corrupted calculation, what does it do?
It will try to fix its position by violently flying 50 feet to the left.
Right into oncoming traffic.
Precisely. That is a multipath flyaway.
That is terrifying.
The drone gets utterly confused by the funhouse mirror of the city canyon. And what makes it so insidious is that your controller screen might show that you have a perfectly healthy connection to 18 or 20 satellites.
So you look at the app, and the app says you're good.
You look at the screen, see the high satellite count, and you feel completely safe. But the drone can't tell that half of those signals are warped reflections.
The signal strength is high, but the quality is garbage.
The quality of that satellite geometry is terrible. Eventually, the mathematical discrepancies become so large that the flight controller's logic gates trip.
It just gives up.
The brain of the drone says, I am receiving completely conflicting location data. I can no longer trust this math to keep the aircraft safe.
And drops into ATTI mode.
And that is the exact moment it drops into ATTI mode and hands the sticks back to you.
Which always happens at the worst possible time.
Of course. It always happens precisely when you are tucked deep into an urban canyon, surrounded by hazards on all sides.
Okay, here's where my brain instantly goes, and I'm sure I'm not alone in this.
Where does it go?
My instinct to mitigate all of this danger is to just go higher.
The altitude myth.
Right. I mean, if I do my site survey and I realize the street level is a multipath nightmare filled with delivery trucks and pedestrians, why wouldn't I just punch the throttle and climb to 150 or 200 feet?
Get away from the mess.
Yeah. I am well above the traffic. I am above the trees. Shouldn't sheer altitude be my ultimate safety net? If I clear the ground hazards, aren't I safe?
It is entirely logical to think that way, but it's a massive trap.
Really? A trap?
Yes. Altitude protects you from one thing and one thing only: the ground.
Okay.
It does absolutely nothing to protect you from side hazards. And a city is not a flat plain with tall grass. It is a complex, three-dimensional, vertical maze.
Right, because the buildings and everything attached to them go up into the sky right alongside you.
Yes. If you are hovering 150 feet up in the air, you might feel like you are in open sky.
It looks clear on the screen.
But if you are only 20 feet away from the sheer facade of a skyscraper, a sudden multipath error or a gust of wind in ATI mode will push you laterally into a glass balcony before you even have time to blink.
You don't have the buffer space.
The vertical environment is littered with side hazards. You have hanging signage.
Yeah.
You have communications antennas sticking out from ledges. You have temporary window washing platforms and construction cranes that swing in the wind.
A lot of metal up there.
And then you have the ultimate, most unforgiving side hazard of all.
Why?
Wires. Wires and thin cables are practically invisible to the human eye. When viewed against a visually noisy, complex background, like a city street.
They just blend in.
Even worse, they're incredibly difficult for the drone's automated optical and infrared obstacle avoidance sensors to detect.
The sensors just look right past them.
Yes. If a gust of wind pushes your drifting drone into a solid wall, you might get lucky, bounce off, and recover.
Maybe break a prop.
Right. But if you drift sideways into a guy wire or a power line, the drone is going to tangle, flip, and go down hard.
There's no bouncing off a wire?
There's no bouncing off a wire. Relying solely on altitude gives you this comforting false sense of security while making you completely blind to the walls that are closing in around you horizontally.
Wow. And speaking of that false sense of security at altitude, the training frameworks highlight something called the rooftop trap.
Oh, this is a big one.
Which I have to admit completely changed how I look at cities.
How so?
Because if I'm flying 200 feet up and I look straight down at a flat commercial building rooftop through my drone's camera monitor.
Right, on the 2D screen.
Yeah, it looks like a safe, empty, gray field in the sky. It looks like the perfect, safe emergency landing zone if things go wrong.
It looks perfect on a two-dimensional screen, but the three-dimensional physical reality is the exact opposite.
It's not flat.
A commercial downtown rooftop is almost never flat or empty. It is a dense, mechanical obstacle farm.
An obstacle farm.
It is heavily littered with massive HVAC cooling units, towering exhaust stacks, taut guy wires supporting antennas,
More wires.
raised parapet walls along the edges, and communication arrays pumping out heavy radio frequency interference that will jam your control signal.
So it's basically a minefield.
But even if you find a clear patch of gravel on that roof, you have to contend with the fluid dynamics of urban wind.
The wind is different up there.
Very different. The edges of flat rooftops create swirling, incredibly violent microcurrents.
Why is that?
When the prevailing wind hits the flat, vertical face of a skyscraper, it has nowhere to go but straight up.
Okay, so it rides up the glass.
It brushes up the glass, hits the roofline, and curls violently over the parapet edge, creating a horizontal vortex.
Like a wave crashing.
Exactly. When your drone was safely in GPS mode, it was actively fighting those violent, invisible currents for you, masking their strength.
And when it drops into ATTI.
The second you lose positioning and drop into ATI mode, that swirling vortex grabs the drone and throws it.
Man.
So retreating toward a rooftop simply because it looks flat and safe on a 2D monitor is often a disastrous choice that pulls you directly into mechanical hazards and extreme wind shear.
So let's look at where we are. We have the perfect storm brewing here.
The worst case scenario.
We have a highly complex, deceptive machine that suddenly drops its automation and fundamentally changes how it flies.
Right.
And we have a hostile, unforgiving 3D environment actively confusing the drone sensors, generating unpredictable wind, and waiting to catch even the smallest lateral mistake.
It's a powder keg.
Now, we have to introduce the most unpredictable, chaotic element of this entire scenario.
The human brain.
The human brain. Why do incredibly smart, well-trained pilots make catastrophic, completely unforced errors in these exact seconds?
It all comes down to psychology.
The training maps out human psychology using a sequence they call the panic chain.
The panic chain is a brilliant way to visualize the psychological sequence of a failure.
How does it work?
It is the predictable way human beings process sudden, high-stakes ambiguity. The chain has 5 distinct sequential links, and if you don't break the chain early, it almost always ends in a crash.
What's the first link?
It starts with link number 1, surprise.
Surprise, okay.
The drone was perfectly stable a second ago, and now it is sliding. The pilot's deeply held mental model, the assumption that the machine will stay where it is put, is instantly shattered.
They're just shock.
This state of cognitive shock immediately leads to link number 2, denial.
Which, you know, when you are sitting in a comfortable chair thinking about it, seems crazy.
Why deny it?
Yeah. You can clearly see the drone drifting toward a building. Why would your brain reject that physical data?
It is actually a deeply ingrained evolutionary protective mechanism.
Really?
Yes. Updating a mental model takes a massive amount of cognitive energy, especially in a high-stress environment. The human brain is efficient. It prefers the status quo.
It's lazy.
So when presented with terrifying new information, the pilot's brain tries to rationalize it away. The pilot thinks, oh, it's probably just a weird gust of wind. The DPS will click back on in a second.
It'll fix itself.
It'll correct itself. I just need to hold on and finish this 5-second cinematic pan for the client.
But in an urban canyon, denial burns time.
And time equals distance. While the pilot is locked in denial, the drone is physically drifting closer and closer to the glass facade.
Closing the gap.
When the pilot finally snaps out of denial and realizes the machine is not going to save itself, they jump to link number 3.
Overreaction.
Exactly. The pilot realizes they're drifting dangerously close to a building on their right, so their amygdala takes over and they physically flinch.
It's a lizard brain.
They slam the control stick hard to the left.
The aviation term used here is stabbing the sticks, right? You are no longer flying the aircraft smoothly. You are just jabbing at the controls out of fear.
Yes, and stabbing the sticks in ATTI mode leads directly to a terrifying phenomenon called pilot-induced oscillation, or PIO.
How does that happen?
Because there is no GPS to act as an automatic brake, when the pilot slams the stick left, the drone banks hard and shoots to the left.
But it carries all that momentum.
Exactly. The pilot lets go of the stick, expecting it to stop, but it just keeps sliding left, overshooting the center point.
Oh, no.
Now the drone is speeding toward a concrete light pole on the left side of the street.
So they panic again.
The pilot panics again, overreacts again, and slams the stick hard to the right. Now the drone shoots back to the right.
Like a pendulum.
In a matter of seconds, the drone is swinging wildly back and forth across the street like an out-of-control pendulum.
And it's all their fault.
And the tragedy is the drone isn't malfunctioning at all. The violent swinging is entirely because the pilot is over-controlling it.
They became the hazard.
In their panic to save the aircraft, the pilot has become the primary source of its instability.
Which pulls us right into the fourth link in the panic chain, fixation.
Fixation is deadly.
And in the context of modern drones, this specifically manifests as screen fixation. The pilot gets overwhelming tunnel vision and stares exclusively at the high-definition video feed on their phone or tablet.
Screen fixation is incredibly common because the screen is deeply seductive.
It looks so good.
It provides a beautiful, bright, clear picture, so your brain is tricked into feeling like the screen is reality.
But it's not the whole reality.
It is a very dangerous, limited sliver of reality. The screen only shows you exactly what the camera lens happens to be pointing at. It does not show you the sheer drop behind the drone. It does not show the overhang directly above it. It does not show the power lines 20 feet to the right.
You're totally blind to the sides.
This is the exact reason why major aviation regulators like the FAA in the United States operating under Part 107 and Transport Canada operating under the CARS framework absolutely mandate visual line of sight, or VLOS.
You have to look at the actual drone.
You are legally required to be able to look up and clearly see the physical aircraft in its surrounding airspace with your naked eyes at all times.
Because the regulators know about this trap.
The regulators understand human psychology. They know that when automation degrades and the drone starts drifting, the screen becomes a liar.
It lies to you.
You cannot assess lateral drift, orientation, or proximity to side hazards by looking at a forward-facing camera.
Yeah.
You have to physically look at the sky to see the truth.
And that screen fixation leads directly to the final fatal link in the panic chain. Bad escape choice.
The worst choice.
Let me throw a very realistic hypothetical your way. Human instinct, honed over a century of traditional aviation, usually dictates that when an aircraft is in trouble, you pull up.
Add power, climb.
You add power and you get away from the hard ground. So if I am flying my drone and it drops into ATTI mode and starts drifting sideways in a tight downtown street, my first instinct is to just jam the throttle stick straight up.
So climb out.
Yeah, I want to climb out of the narrow street canyon, get above the rooftops, and find safe open air. Why is that natural instinct a bad escape choice?
Because a blind climb in an urban environment is essentially playing Russian roulette.
Really?
We have to remember the concept of the 3D maze. When you are staring down at your screen in a panic and you push that left stick straight up to climb, you have absolutely no idea what is occupying the airspace directly above the drone.
Because the camera is looking forward.
Right. You might punch the throttle and climb straight up into the steel underside of a window washing crane that was extended from the roof.
Just smash right into it.
You might climb directly into a web of unseen communication wires strung between two buildings.
Or the wind shear we talked about.
Exactly. Or, even if the airspace is physically clear, climbing out of the sheltered street level might punch you directly into a massive 50-mile-an-hour wind shear that exists unobstructed above the roofline.
And then it's just gone.
That wind will catch your ATTI mode drone and immediately blow it completely out of your operating area over pedestrian zones or traffic where you have zero chance of recovering it.
So pulling up is terrible.
In a city, you simply cannot move first and think second.
The training frameworks really drive this home with a chilling scenario they call the downtown orbit.
Oh, this scenario gives people nightmares.
I want everyone listening to put themselves in this pilot's shoes. Imagine you were flying a perfect, automated circular orbit around a gorgeous, historic clock tower in the center of town.
Very common shot.
The camera on the front of your drone is pointed sideways, constantly locked onto the center of the clock face as the drone flies sideways in a circle.
Doing its automated orbit.
Right. You're staring down at this beautiful, smooth, stable video feed on your controller screen. It looks like a movie.
You feel like Spielberg.
You do. But you have no idea that the GPS signal just degraded due to multipath reflection from a nearby office building.
The funhouse mirror strikes.
Right. The drone drops into ATTI mode. And because the drone's camera is looking to the left at the tower and the wind is blowing from the left, the drone is physically being pushed backward.
Drifting blind.
It is drifting completely blind, tail first, straight toward a concrete light pole on the edge of the square.
And you can't see it on the screen.
You are standing there admiring your cinematography on the screen, feeling like a genius, while the physical machine is 2 seconds away from shattering into 100 pieces.
And what are you doing?
And instead of flying the drone, what are you doing? The training calls it arguing with the app.
Arguing with the app is such a brilliant descriptive phrase for this modern phenomenon.
What does that mean exactly?
The pilot is looking at the screen, and suddenly a warning flashes over the video feed. Maybe it says compass error, or weak GNSS, or vision sensors disabled.
A little pop-up box.
Instead of immediately looking up at the sky and taking manual control of the physical aircraft, the pilot stays glued to the screen and starts tapping the glass.
Trying to dismiss it.
They start swiping away menus. They try to hit the little X to dismiss the warning so they can see their shot again.
Wow.
They tap on the satellite icon to see how many bars they have. They're literally hoping that by interacting with the software UI, they can somehow resolve a physical aerodynamic physics problem that is occurring in the real world.
You're swiping while the drone is crashing.
You are wasting the most precious seconds of the emergency trying to negotiate with the user interface while gravity, momentum, and wind are actively taking command of your aircraft.
Okay, so we have deeply diagnosed the panic. We know exactly how the links of the chain snap together to wrap around a pilot's neck.
We know the trap.
We understand the trap. Now we need the cure.
Time for the playbook.
We are moving into the practical application. How exactly does a stone-cold veteran professional recover the drone when every fiber of the panic chain is screaming at them to flinch and stare at the screen?
It takes discipline.
The framework for this starts with what is called the 5-second mental switch.
The 5-second switch is an intentional, aggressive, and immediate cognitive shift.
You have to force it.
In the span of 5 seconds, you have to completely abandon your identity as a creative camera operator and instantly adopt the identity of an aviator.
You're not a photographer anymore.
You have to mentally let go of the cinematic shot you were trying to get. You have to let go of the money, the client's expectations, the lighting, everything.
Just drop it.
Your brain must forcefully transition from the goal of capture the shot to the absolute imperative of control the aircraft.
Because if you try to do both...
If you do not make this mental switch instantly, you will try to divide your attention to serve two masters, and you will fail catastrophically at both.
The frameworks outline an exact step-by-step recovery flow that you have to execute in those crucial 5 seconds.
A physical checklist.
And step 1 is fascinating to me. Step 1 is name it. You don't just think it. You literally speak out loud.
Yes.
You say positioning degraded, stopping capture. Why is it so mechanically important that I physically talk to myself in an emergency?
It is entirely about neurology. Speaking out loud engages the motor cortex and different language centers of your brain.
Oh, interesting.
This physical act of vocalization forcefully shatters the denial phase of the panic chain.
It grounds you.
It interrupts the amygdala's fear loop and forces your conscious brain to acknowledge the objective reality of the situation.
Because you heard yourself say it.
Furthermore, saying it out loud immediately communicates critical information to anyone standing near you, specifically your visual observer or your client.
You're claiming the airspace.
It instantly signals that the parameters of the mission have changed. You are letting them know, I am no longer adjusting the camera framing. I am actively managing an aviation emergency. Give me space.
That makes perfect sense. You break the denial by making it real in the air.
Exactly.
Step 2 in the flow. Eyes outside. You tear your gaze away from that seductive lying screen, and you physically locate the drone in the physical sky.
Establish VLOS.
Step 3, smooth inputs. You do not stab the sticks. You assess the direction of the drift, and you gently apply sustained counterpressure to arrest the momentum without inducing that violent pendulum swing.
Fly the aircraft, don't flinch.
And then we reach step 4, which the training presents as the absolute golden rule of urban drone recovery. Create separation.
The most important rule.
The guiding motto here is space before home.
Space before home is arguably the single most vital concept in this entire urban playbook.
Unpack that. What does that mean?
When things go wrong, a panicked pilot's overwhelming instinct is to immediately try and bring the drone back to the exact spot it took off from.
Back to the launch pad.
They mentally view home, the launch pad, as the ultimate magical safe zone.
Right. If I can just get it back here, I'm safe.
But you have to realize that home is just an arbitrary geographic coordinate on a map.
That's true.
Space is what actually provides safety. If your drone loses GPS and is drifting 10 feet away from a massive glass building, and your launch pad is 50 yards away down a narrow street,
Your first move shouldn't be towards the street.
your first stick input should absolutely not be toward the launch pad. Your first move must be directly away from the highest consequence hazard.
Just push it away from the glass.
You push the stick laterally to move the drone into open air. You want to create a buffer of space around the aircraft.
And why is that space so important?
Once you have 30 or 40 feet of clear, open air in every direction, you have bought yourself the most valuable resource in aviation.
Time.
Time to think. Once you are hovering safely in that pocket of space, you can stop, take a deep breath, assess the wind direction, check your battery life, and then logically figure out how to navigate the drone back to the ground.
But wait, I have to bring up the ultimate technological safety net that every drone pilot knows about.
I know where you're going.
Every modern prosumer and professional drone has a dedicated panic button right there on the face of the controller.
The RTH button.
The return to home button, the RTH. If I am out there flying, I get disoriented, the drone drops into ATTI mode and starts drifting, and I follow your advice to create a pocket of open space.
Okay, you're hovering in space.
Once I have that space, why wouldn't I just smash that RTH button and let the drone's incredibly smart computer figure out the math and fly itself safely back to my feet?
Because treating the RTH button as a magic savior is the ultimate myth of drone automation.
A myth.
To understand why it's dangerous, you have to understand how the return to home function works mechanically.
How does it work?
The RTH system relies entirely, 100%, on the drone's GNSS system to function.
Oh no.
It needs GPS to know exactly where it currently is in the sky. It needs GPS to know the exact coordinates of where the launch pad is. And it needs GPS to calculate the navigational flight path between those 2 points.
So if the GPS is degraded,
If your in-flight emergency was initially caused by a GPS dropout, severe multipath reflection, or compass interference, hitting the RTH button is the equivalent of asking a deeply disoriented, blindfolded person to drive you home in the middle of a blizzard.
oh wow. That is a terrifying analogy. You are desperately asking the broken system to save you by relying on the exact same broken system.
Yeah, exactly. The drone's internal map might be completely corrupted. It might calculate that the fastest way home is a straight line that goes directly through the center of a glass office building.
And it'll just ram right into it.
And because you commanded it to return home, it will aggressively bank and accelerate right into that glass.
What if the GPS kind of comes back?
Even if the GPS signal briefly reconnects and seems healthy, the automated straight line path back to your launch pad might take the drone completely blind through a power line or a tree canopy that it can't see.
Because it's just flying a dumb straight line.
The RTH button is a highly useful tool in very specific situations, like losing your radio control link in an open field. It is not a magic wand.
So what do you do instead?
Before you ever press that button in a city, you must run through a mental checklist known as route, trust, height.
Route, trust, height. Let's break down exactly what a pilot needs to process for each of those.
That's a rapid gonna-go assessment.
Okay, route.
Route. Look at the physical environment. Is the direct straight line path between the drone's current position in the sky and the home point completely clear of vertical obstacles? Are there any buildings, cranes, or wires in the way?
Okay, trust.
Trust. Look at your telemetry. Do you currently trust the drone's positioning data? Is it showing a strong, stable connection to 15 or 20 satellites without any compass warnings or multipath bouncing? Height. Look at your settings. Is the drone's pre-programmed RTH altitude set high enough to safely clear all the structures between you and the drone, but low enough that it won't climb into controlled commercial airspace or dangerous high-altitude wind shears?
That's a lot to process.
If you cannot instantly and confidently answer yes to all three of those questions, you must keep your thumb off that button and fly the aircraft back to the ground manually.
And flying it back to the ground manually brings us to a concept called the alternate landing zone rule.
This is a lifesaver.
You touched on this earlier when you mentioned that panicked pilots get fixated on bringing the drone back to the exact spot they launched from. Why is that homing instinct such a dangerous problem in an urban environment?
Because it is an emotional attachment, not a logical aviation decision.
Emotional?
The pilot feels this immense psychological pressure to finish the job cleanly. They feel like the flight is a messy failure unless the drone lands squarely back on the little orange landing pad they meticulously set up on the sidewalk.
It's an ego thing.
It is. But think about the physics and the geometry of the situation. Suppose you launched your drone from a narrow, wind-tunneled alleyway, flew out into a wide-open square to get your shot, and then suffered a GPS dropout.
Okay.
You managed to arrest the drift and create space in the open square. But then, to get back to your launch pad, you have to manually fly an unstable drifting drone back into that narrow, treacherous alleyway.
Which makes no sense.
You are intentionally forcing a degraded aircraft through a high-risk choke point, simply out of geographic stubbornness.
So how does a professional handle it?
A professional pilot actively trains to break that emotional attachment. During the pre-flight site survey, hours before the drone even powers on, a professional identifies their primary launch pad, but they also physically walk the area and identify 2 or 3 alternate wide-open landing zones.
They pre-plan the bailouts.
It might be a nearby empty parking lot, a wide stretch of park grass, or a flat, empty cul-de-sac.
Anywhere safe.
The rule they follow is ruthlessly simple. In an emergency, the safest place to land is wherever you can get the aircraft on the ground, with the absolute least amount of kinetic risk to people and property. Period.
Doesn't matter if it's far away.
It does not matter if that alternate landing zone is 2 blocks away and you have to walk to go pick up the drone. A safe landing is a safe landing.
Okay, so we are visualizing this scenario. The GPS dropped out. You made the 5-second switch. You didn't flinch. You got your eyes outside. You applied smooth inputs. You created a buffer of space. You ignored the RTH button. And you are slowly walking the drone down toward a safe alternate landing zone.
Textbook recovery.
But here is where the mechanics of professional operation get really interesting, because you are rarely flying in a vacuum.
No, you're in public.
There are almost always other human beings standing right next to you on the sidewalk. And managing those people is just as critical as managing the aircraft.
Crew resource management.
Let's dive into the crew dynamics, starting with the visual observer, the VO. What is their actual functional job during a flight? Because I feel like a lot of newer operators treat the VO as just a buddy in a high-vis vest who gets to hang out and watch the cool drone fly.
Treating the VO as a spectator is a massive failure of crew resource management.
They're not just a buddy.
A visual observer is a critical, highly active safety tool. In fact, in many complex operations or flights near people, a VO is explicitly mandated by aviation regulations.
So what are they supposed to be doing?
Their primary job is to maintain constant visual line of sight on the aircraft and scan the surrounding airspace for intruding helicopters, birds, or changing weather, and to communicate those dynamic threats to the remote pilot in command.
Okay.
But the way they communicate is what truly separates the amateurs from the professionals.
The training frameworks draw a very sharp, distinct line between core cockpit language and professional tactical language.
Yes, language matters.
Give me a scenario. What does poor amateur language sound like during an emergency?
Poor language is vague, highly emotional, and it forces the pilot to use their already limited brain power to process unnecessary information.
What's an example?
Imagine the drone drops into ATTI mode and starts drifting. The amateur VO says something like, hey man, something is weird up there. Hold on, I think it's moving. Are we okay? What's the app saying? Did you hit a button?
Oh man, that would drive me crazy.
That kind of chaotic chatter injects pure cognitive noise right into the pilot's brain.
It's just a distraction.
The pilot is already completely task-saturated. They are actively trying to process wind speed, momentum, lateral drift, and stick inputs. They absolutely do not have the cognitive bandwidth to decipher what the phrase "something is weird" actually means in physical space.
So to fix that, what should the professional VO sound like?
A professional VO sounds like a calm, calculating machine. They use short, declarative, actionable statements devoid of any emotion.
Like what?
They say things like drift left, building, closing right, 20 feet, clear right, people entering below, hold position, alternate landing zone open.
Wow, so precise.
That is professional tactical language. It gives the pilot exactly the spatial data they need to make a physical control input and absolutely nothing else. A great VO effectively turns themselves into an external wide-angle sensor for the pilot's brain.
Okay, the VO is disciplined. They are feeding you good data. But what about the person who is actually writing the check, the client?
The client.
Let's do a little role play here to illustrate the pressure. I'm going to be the demanding, high-paying corporate client standing right over your shoulder looking at the monitor.
Bring it on.
The drone just slipped into ATTI mode. You, the pilot, executed the playbook perfectly. You yelled, "Positioning degraded, stopping capture," and you smoothly flew the drone 30 feet away from the skyscraper facade to create space.
Safe and separated.
But I am looking at the monitor, and the framing of the building is gone, and I say, "Whoa, whoa, whoa, what are you doing? Why did you move it?" The lighting on the glass is absolutely perfect right now. The sun is setting, the drone is still in the air, the battery says 50%. Can't you just push through this glitch and finish the last 5 seconds of the pan? We really need this shot for the commercial.
That right there is the ultimate pressure cooker.
It's hard to say no to the person paying you.
And as the pilot holding the sticks, you have to deeply internalize the fact that the client does not understand aviation risk.
They just want the pretty picture.
They don't know what ATI mode is. They only understand the aesthetic value of the video feed. But in that moment, you are not just a creative director holding a camera. You are the remote pilot in command of an aircraft.
You're the captain.
And the federal regulations, whether it's Part 107 in the U.S. or Sirhar 101.16 in Canada, are explicitly written to empower and protect you in this exact high-pressure moment.
They give you the authority.
Those rules clearly dictate that the remote pilot in command has the final, unquestionable authority to cease any operation if safety is compromised.
So you don't have to listen to the client.
You, the pilot, legally own the airspace outcome and the liability. The client does not.
Right. If it crashes, it's your license on the line.
Exactly. So your response to that client is critical. You do not argue with them about the lighting. You do not apologize for ruining the shot.
You don't say sorry.
And you absolutely do not ask for their permission to land. You use a pre-planned psychological script designed to project absolute command of the situation.
And the training frameworks actually provide the exact script to use to diffuse that tension. Let me read it out because the phrasing is very deliberate.
Okay.
We had a positioning reliability issue, so I stopped the shot and recovered the aircraft safely. In this urban environment, a small drift can become a bigger issue very quickly. I will reassess the flight path, check the telemetry, and we will continue only if we have enough margin to do it safely.
I want you to notice exactly what that script accomplishes linguistically.
It's very dry.
First, it doesn't sound panicked. It sounds incredibly boring, methodical, and procedural. And in a moment of ambiguity, boring and procedural is exactly what a client needs to hear to feel like they're in safe hands.
They want to know you're in control.
You clearly state the technical problem without exaggerating. Positioning reliability issue. You state the definitive action you took recovered safely.
Right.
You explain the logical reason for the action. Drift becomes a big issue quickly. And you outline the immediate path forward. Reassess and continue only if safe.
You're taking charge.
You project absolute undeniable competence. You prove to the client in real time that you are prioritizing the safety of the public and protecting their corporate liability over getting a pretty picture of a sunset.
Which they should appreciate.
A true professional would always, 100% of the time, rather disappoint a client with a missing shot today than have to explain a catastrophic collision to the aviation authorities tomorrow.
That script is a masterclass in establishing professional boundaries.
It really is.
Okay, let's play the scenario out to the end. You manage the drone's drift. You manage the VO's callouts. You managed the client's expectations, and you successfully walked the drone down to a safe alternate landing zone in an empty parking lot.
Touchdown.
The motors cool down, the adrenaline slowly starts fading from your bloodstream. You survived the urban canyon.
You could finally breathe.
But the training dictates that the mission isn't actually over yet.
Not even close.
In fact, what you choose to do in the next 24 hours determines if you are truly a professional aviator or if you were just a lucky amateur who dodged a bullet. We are entering the final phase, the competence loop.
The competence loop is the framework for turning a terrifying scare into a permanent skill.
How does it work?
When a weak reactive pilot survives a severe GPS dropout, they pack up their gear, wipe the sweat off their forehead, throw the drone in the trunk and say, "Wow, we got lucky today. Let's hope that never happens again."
Just writing it off as a fluke.
They learn absolutely nothing from the event. They just survive by the skin of their teeth, and they subconsciously adopt the dangerous assumption that the universe will just protect them next time.
Which is a bad assumption.
Sociologists call this the normalization of deviance, accepting a near miss as a normal part of doing business.
But a professional operator treats a near miss as a goldmine of raw, actionable training data.
Exactly. A professional pilot debriefs the event ruthlessly, either by themselves or with their crew. They sit down and ask the hard, uncomfortable questions.
Like what?
What was the very first environmental clue I missed? Did the drone feel soft on the sticks 10 seconds before the warning flashed? And did I ignore it?
Right.
Did I succumb to screen fixation and stare at the tablet for too long? Was my escape route pre-planned and briefed? Or did I just make it up on the fly in a panic? Did my visual observer use crisp tactical language? Or did they hesitate?
You dissect the whole thing.
A near miss isn't just a fluke. It is the aircraft and the environment, showing you exactly where your assumptions were wrong and highlighting exactly where your manual stick skills are currently the weakest.
And the frameworks emphasize that you absolutely cannot practice and refine these manual stick skills in the middle of a dense urban canyon.
No, do not practice in a city.
You don't wait for a crisis to figure out how to fly without the GPS safety net. You take the drone out to a massive, empty, safe, grassy field on a windy Saturday. You manually switch the drone into ATTI mode, and you run drills.
Drills.
The training provides 6 specific mechanical drills to build that muscle memory. Let's really dig into these so people understand the physical mechanics of what they need to practice.
Okay, let's do it.
Drill 1 is the orientation triangle. You practice hovering and flying the drone nose in, tail in, and side on. I want to talk about nose in flying. Why is flying with the camera facing you so incredibly difficult for the human brain to process in an emergency?
Because it creates massive cognitive dissonance.
How so?
When the nose of the drone is pointing directly at you, the lateral controls are completely reversed from your physical perspective.
Oh, right, because it's facing backward compared to you.
Imagine the drone is facing you, and a gust of wind starts pushing it to your left.
Yeah.
Your eyes see the drone moving left.
Right.
Your panicked brain defaults to your own body's perspective, so you intuitively push the right stick to the right to counteract it.
Seems logical.
But because the drone is facing you, pushing the stick to your right commands the drone to move to its right, which is your left.
Oh man, so you just double the speed into the drift.
So by trying to correct the drift, you actually accelerate the drone twice as fast in the wrong direction. If there's a building on your left, you just flew the drone straight into it.
That is brutal.
You have to drill the orientation triangle over and over until reversing those controls becomes subconscious instantaneous muscle memory. You cannot afford to spend 2 seconds doing the mental gymnastics of, okay, it's left is my right, when the drone is drifting toward a window.
That makes total sense. You have to reprogram your instinct.
Yes.
Drill 2 is the smooth stop. This is learning to brake gently without overshooting. And in ATI mode, this means you can't just let go of the stick. You have to apply reverse thrust, right?
Right.
But if you pull back too hard, you induce that pendulum swing we talked about.
Exactly. The smooth stop drill is all about learning the exact aerodynamic momentum of your specific aircraft.
So feathering the stick.
If you are flying forward at 15 miles an hour in ATTI mode and you want to stop, you have to practice feathering the stick backward just enough to pitch the drone up and use the thrust as a brake, holding it there until the forward momentum bleeds off, and then smoothly returning the stick to center so it settles into a hover.
It's an art.
It requires a delicate touch that most pilots never develop because the GPS usually does it for them.
Drill 3 is drift correction. This is essentially learning to hover visually in the wind without chasing the drone back and forth.
Right. It's about station keeping. You put the drone in ATTI mode in a 10-mile-an-hour wind, and you try to keep it perfectly hovering over a specific patch of grass.
Anticipating the wind.
You learn to make micro-adjustments, anticipating the gusts rather than just reacting to them after they push the drone.
Drill 4 is escape direction. This one requires a VO. You are flying along, and your helper suddenly yells out an obstacle like, building left or wire right.
And you have to react.
And you have to instantly process that audio cue and choose the correct escape vector to push the drone into space.
This drill builds the neural pathway between hearing a command and executing the correct stick input without hesitation. It removes the processing lag that causes pilots to freeze.
Drill 5 is the alternate landing, literally forcing yourself to land the drone somewhere other than your primary launch pad just to break that emotional attachment.
Prove to yourself that the drone works just fine landing on a different patch of dirt.
Exactly. And finally, drill 6 is crew callouts. Sitting down with your VO and practicing that crisp, robotic, professional language until it feels natural.
Getting the communication dialed in.
But hearing all of this, looking at all this intensive training, I have one final pushback for you.
Let's hear it.
If I spend weeks doing all these drills, if I master the orientation triangle, if I become an absolute savant at manual ATTI flight, isn't the ultimate goal to become so incredibly good that I never experience a GPS dropout or near miss ever again?
That assumption right there is what aviation experts call the pro trap.
The pro trap.
And it is arguably the most insidious, dangerous illusion of all, because it specifically preys on highly experienced, highly skilled pilots.
Why is it dangerous to be good?
The pro trap is the false belief that because your manual stick skills are flawless, you can logically accept thinner safety margins in your operation.
Oh, I see.
A pilot falls into the pro trap when they think, I am a master at A-mode recovery, so it's perfectly fine for me to fly this tracking shot just 3 feet away from this glass building instead of 30 feet away. Because if the GPS drops, I have the lightning-fast reflexes to catch the drift before it hits the glass.
You get arrogant.
That mindset is completely backwards. It is using skill to justify unnecessary risk.
As you said earlier, true experience should create better margins, not thinner margins.
Precisely. A true master of aviation does not use their high skill level to justify flying in stupid, unnecessarily hazardous ways.
What do they do?
They use their vast experience to design operations that avoid needing a heroic, pulse-pounding recovery in the first place.
They design the risk out of it.
A master builds in massive standoff distances during the planning phase. They map out perfect, unobstructed escape routes before the drone even powers on. True mastery is actually making the operation look incredibly boring to an outside observer.
Boring is good in aviation.
It looks boring because the master pilot has systematically identified and eliminated the risk variables before the drone ever leaves the ground.
The training frameworks synthesize this entire philosophy by breaking recovery down into 3 distinct escalating levels.
The 3 levels of recovery.
Level 1 is aircraft recovery. Can you manually fly the physical drone to the ground safely during an emergency? Most amateur pilots stop right there. They land, they pack up, they go home.
And they think they won.
Level 2 is mission recovery. Once the aircraft is safe, can you manage the client's emotions, redesign the flight path on the fly, move your launch point to a better location, and try to capture the shot again safely?
That's a higher level of competence.
The level 3 is where the true professionals live. Level 3 is system recovery. Can you take the terrifying data from what you just learned, go back to your office, and permanently rewrite your company's standard operating procedures so that this exact scenario never scares anyone on your team ever again?
That is the holy grail.
Let's use the final scenario from the text to paint a complete picture of what level 3 looks like in the real world.
Walk us through it.
Imagine you are doing a real estate architectural shoot near a local school. You are flying low over a row of houses. Suddenly, the drone loses GPS due to local interference and drops into ATTI mode. The wind catches it, and it starts drifting sideways toward the roof of a house.
Classic scenario.
Because you are trained, you execute the playbook perfectly. You verbally say, positioning degraded, breaking your denial. You get your eyes outside off the screen. You apply smooth counterstick inputs.
Nice and smooth.
You push the drone away from the house to create a buffer of space, and instead of trying to fly it all the way back to the client's narrow driveway, you land the drone safely in the wide-open, empty school athletic field next door.
Alternate landing zone. Perfect.
You handled it. The aircraft is safe. But the ultimate win in this scenario isn't just that the plastic drone isn't broken.
Now it's what comes next.
The ultimate win is that the next morning, you go into your office, you pull up your company's pre-flight briefing template document, and you explicitly type in a brand new rule.
You change the system.
You add a line that says, abort trigger. Any unexpected lateral drift near residential structures equals an immediate stop capture command and a mandatory diversion to an alternate landing zone.
You literally rewrite the rules of engagement.
You update the operational system. And then, that afternoon, you take your drone out to an empty park and spend an hour practicing nose-in hovering to make sure your reflexes are sharp. That is level 3 recovery.
It is the complete, holistic life cycle of professional competence.
Yeah.
You aren't just surviving the hostile environment. You are actively adapting your entire operational methodology based on the harsh data the environment provides.
You evolve.
You move from being a reactive drone operator who hopes for the best to a proactive aviation professional who engineers safety.
So, as we pull all these threads together, what does this actually mean for us? Let's recap the intense journey we just took through the urban sky.
It's been a ride.
We started with the stark realization that the managed flight provided by modern GPS algorithms makes flying feel incredibly easy, but it masks a dangerous illusion of mastery.
It tricks our brains.
When you fly into the compressed, hostile geography of an urban canyon, the glass, the steel, and the severe multipath reflections act like a funhouse mirror, confusing the drone and forcing it to drop its automated hold.
The environment attacks the sensors.
When that happens, the city compresses your available time and space, instantly turning a minor 3-meter drift into a high-speed collision path.
The margins vanish.
We explored the chaotic human factor, how the brain's shock leads to denial, which leads to overreaction, the pendulum swing of pilot-induced oscillation, the fatal trap of screen fixation, and the terrible instinct to climb blindly into unseen hazards.
The panic chain.
But we also mapped out the discipline cure, the immediate 5-second switch from capturing a shot to controlling an aircraft.
From photographer to aviator.
We learned the absolute necessity of prioritizing open space before trying to return home. The myth of the RTH panic button, the art of communicating like a cold, calculating professional with your crew and your clients.
Setting those boundaries.
And finally, the discipline to use a near miss as raw fuel for the competence loop, rewriting your standard procedures and ruthlessly drilling your manual skills.
The essential through line across all of this material is that the machine, no matter how advanced, is merely a tool.
It's just a tool.
It is not a savior. The GPS helps you, the sensors assist you, but at the end of the day, you are the pilot in command. And real, tested professionalism begins precisely in the terrifying fraction of a second when the automation stops helping.
Which brings us to a final, slightly broader and provocative thought for you to mull over as we wrap up this deep dive.
Oh, I'm ready.
Today, we spent our time talking entirely about camera drones, multipath satellite signals, and the aerodynamics of urban canyons.
Very specific aviation stuff.
But this core psychological concept of managed flight, the seductive trap of trusting invisible, complex systems to do the hard balancing work for us, is absolutely everywhere in our modern lives.
Oh, wow. Yeah.
Think about the GPS navigation app on your phone that you blindly, unquestionably follow, even when it nonsensically routes you into strange neighborhoods, closed roads, or massive traffic jams.
We all do it.
Think about the pervasive spell check and grammar algorithms that quietly fix our writing in real time, slowly eroding our actual manual grasp of language and syntax.
Right, the invisible safety net.
Think about the highly curated social media feeds that automatically filter, shape, and deliver our worldview, or the new AI tools that are increasingly drafting our emails, summarizing our complex meetings, and even doing our initial creative thinking for us.
It's all managed flight.
In almost every sector of society, we are increasingly becoming passive supervisors of automated systems rather than doing the actual manual driving ourselves.
We're just supervising.
And just like with the drone hovering over the city street, this constant supervision creates a massive, comforting, false sense of mastery. We think we are highly capable, but the machine is doing the heavy lifting to mask the wind.
It's masking our lack of skill.
So as you go about your week, ask yourself this. In what other critical areas of your daily life has invisible automation quietly turned you into a lazy pilot?
That's a great question.
You might feel like you are in total control of your career, your information diet, or your skills, but are you really just floating on ATTI mode, relying entirely on an invisible algorithm to hold your position against the wind?
And what happens when it drops out?
Exactly. If the GPS of your daily technology drops out completely tomorrow, if the power grid goes down, if the app server crashes, if the AI begins to hallucinate and feed you corrupted multipath data, do you still possess the raw, manual stick skills required to navigate your life, arrest your drift, and avoid a catastrophic collision?
Something to really think about.
Thanks for joining us on this deep dive. Keep your eyes outside, trust your instruments, but verify with your own senses, and we will see you next time. That's a wrap on today's mission, Commander. See above, go beyond, get ahead. For more training, tools, and intel, head to skycommander.ca. If you learned something new, share it, subscribe, and leave us a 5-star debrief.